Okay, to design the pressure vessel which is subjected to the external pressure. Okay, previously we have learned that the pressure vessel which is subjected to the external pressure for the vacuum condition which has the maximum pressure of 1 atm or 1 bar, and we have the jacketed vessel. So basically these are the example or the application of the pressure vessel which is subjected to the external pressure. Okay, the thin wall vessels subject to external pressure are liable to failure through elastic instability, we call as buckling. And it is this mode of failure that determine the wall thickness required. So you may refer to this, okay, this is before the incident and this is after the incident. Okay, this is due to the air pressure surrounding this vessel. So this is the instability of the elasticity due to buckling. So that's why in designing the pressure vessel, we gonna refer to the calculating on the critical pressure or related to the buckling. So for the determine the buckling or the critical pressure for the open-ended cylinder, you may use this equation. So we can see here we have the consideration on the external diameter, the length of the vessel, a Young modulus or related to the elasticity due to the pressure effect, and also the Poisson ratio. Okay, this is the general equation, but it can be simplified into this equation. So for the long tubes and cylindrical vessel, so we can neglect this term and it turns to this equation. Okay, for the minimum value of critical pressure will occur when the number of loops, which is n equal to 2, and we can simplify the equation by inserting n equal to 2 to this equation. And for the most pressure vessel material, we may use Poisson ratio equal to 0.3 and the simplified version of the equation to determine the buckling or the critical pressure. Okay, for short closed vessel and long vessel with stiffening. Okay, stiffening is the another support that we have this stiffening for the long vessel and the closed vessel to support this the vessel which is subjected to the external pressure. It can protect the vessel from any collapse. So the effect of stiffening can be taken into account by introducing the collapse coefficient or denoted by Kc. So the value of Kc can be referred to this figure. So we have the effective length raised to the outside diameter, and then we can obtain the value of Kc here. So insert this value into this equation and we can obtain the value of critical pressure. Okay, this is the typical arrangement for the effective length. So we have this is effective length and H over 3 to obtain this height of the pressure vessel. And Ls is the length of the stiffening ring. So this is the stiffening ring, and usually the effective length equal to the stiffening ring. So this is how we can determine the length of the effective length from the pressure vessel. Okay, next to determine the thickness for the vessel head. Okay, the minimum thickness to design head or vessel under external pressure can be obtained using this equation by considering the Young modulus, the external pressure, and also the radius outside the or shell radius. So from this, we can obtain the thickness of the head of the vessel. But this is for the initial estimate only. You may refer to the ASME boiler pressure vessel code for the detailed design.